Hello, welcome to everyone to my YouTube channel. So in this class, I will teach about the NMR spectroscopy. So how the NMR intensity of the uh, signal with the intensity of the NMR signal depends. So first, in this example, the neopentyl chloride. So let's how to try look into another most important metrics in comparing data intensity of NMR signal. Say we have two sets of non-equivalent proton in a molecule. So if the number of equivalent proton in one set is higher than that of in another set, undoubtedly the intensity of the signal with the higher number of equivalent protons will be higher than of the other. This is due to the fact that for the former number of nickel in one state is higher than of the latter. Undoubtedly, the area under the NMR signal representing the intensity of the absorption is directly proportional to the number of protons giving rise to the signal. So that means so that means the number of protons in one particular set is higher compared to the other set. So that higher number of protons will give higher intense NMR signal in the NMR spectrometry. So let's say the example, it is a neopentyl chloride. So in the neopentyl chloride, it has two types of sets of equivalent protons. So on all these 9 proton that comes as a give one signal, and these two H2O give one signal. So here this methyl group, a total 9 protons, it will appear at 0.94 ppm, and on methylene group having 2 anisotropic protons that appear at 330 ppm. So after the spectrum is determined, it is indicated for the particular absorption by the instrument to determine the area of the under signal. The integral tracing usually records from left to right, digitally at the bottom of the peak. Sometimes the height that the tracing rise for each group of proton is proportional to the area enclosed by the peak, and therefore to the number of protons responsible for their absorption. Hence, here the spectrum will show two absorption peaks having the ratio 1:4.5, indicated the presence of 2 and 7 equivalent protons and 9 methyl protons. So here these 9 proton comes in this region and these two. So here the intensity is 2:9. That means 1:4.5. So this is the ratio of the peak intensity of this compound. Similarly, for this compound, sector of the symmetrical paraxylene. This is a paraxylene. So in this case, paraxylene, here total 2 sets of proton. One set it has total 6 proton, so it is come as 2.34, and this is for the 6 proton, and here total 4 aromatic proton that will come as the 4 aromatic proton. So here peak intensity is equal to 4:6. That means 2:3. So here this is a mesitylene. So mesitylene has total 2 sets of proton. This 3CH3 proton will come at 2.34 from 9 proton, and these 3 aromatic proton will come at 7.16. So here the ratio is 3:9. That means 1:3. So here total 6 peak intensity is 1:3. And another example is the 3-chloro 2,2,4 tetra methyl pentene. So here total 2 sets of proton. Here all these CH3 group are equivalent. So here total 3, 3, 6, 9, and here 9, total 18 proton. On here total 1 proton. These 18 proton come at 0.994, and these methylene proton come as 3.4 to 1. So here ratio is to 1 is to 18. So from these above three examples, it is obvious that the peak heights are in the ratio of the number of two sets of non-equivalent proton. So let's put one example NMR spectra of ethanol. So ethanol under low resolution spectra absorption 3. So in the ethanol there are three types of proton. One is 3H3 proton and 2 CH2 proton and 1 H proton. So here the proton intensity 1 is to 2 is to 3. So here spectrum shows 3H3, the area was ratio 1 is to 2 is to 3. So corresponding to 1 proton per OH and 2 proton per CH2 and 3 proton per CH2. Respectively, an OH proton absorbs downfield from TMS 5.37 and proton CH2 3.62 and CH3 is 1.17. So this is the NMR spectra of the ethanol molecule. So here molecule. This is for the 1 proton, this is for 2 proton, and this is for 3 proton. So here the peak intensity is 1 is to 2 is to 3. So in this spectrum of ethanol, integer tracing drives 6 by 12.4 square for the OH, CH2 respectively. These correspond to relative proton count for 1 is to 2 is to 2.97. When the equivalent integration strength, it is useful to set the smallest integration of a unity to convert in the other value proportionally. So now I will discuss one problem. So a compound, a molecular formula of C1180 shows the absorption at 1.28 and 2.28 and 7.1 respectively. The ratio of the step heights of the three types of non-equivalent proton is 8.8 is to 2.9 is 2.8. How many number of each kind of proton will be present and what will be the possible structure of the compound? So the compound formula is C11H80 and they have three types of proton. So the peak intensity height is 8.8, 2.9 and 3.8. So the compound molecular formula is, so it is a solution. So compound molecular C880 contains 3 non-equivalent. Let us consider the 3 non-equivalent. One is A, one is B, one is C. So now the given number of ratio of the 3 height signals are A is to B is to C is equal to 8.8 is to 8.9 to 3.8. So here total number of total number of proton is 16. So here we have to first add all these things. So here it is come as 15.5 and total number of proton in this molecule is C11H16. That means 16 electron, 16 proton. So since the molecular formula is C11H16, so the number of hydrogen per unit of the height, so A equal to 1. So number of hydrogen per unit is, so we have to divide it 16 by 15.5, that is 1.03 hydrogen per height. So for A, for N, there for A, their total number of proton is 1.03 into with 8.8, so 9.1 is, so that is close to 9. For B, there's total 1.0 into 2.9, that is 3 hydrogen. And for C, 1.03 into 3.8, that is 3.9, this is 4 hydrogen. So here total A type of proton is 9, B type of proton 3, and C type proton is 4. So now the saturated analog of the given compound has the molecular formula as C11H24. So the efficiency of the H atom is 20.8. Thus the compound may contain a benzene ring. According to the problem, the absorption peak 1.28 delta A or 2.2B delta C and 7.08 delta E. So the 4H of C absorbed in the aromatic range 7.1. arresting the distributed benzene C6H4. So 3HB for day 2.28 indicate the presence of CH3 group at the benzylic position, and so given lastly the equivalent 9H associate nearly normally alkyl group 1.28, and there must be tert-butyl group. So the compound is the tert-butyl toluene. So here this A is 9 proton for the A, that will come as 1.28, and the CH3 come as 3 proton for that is 2.28, and they have total 4 aromatic, so here that will come at 7.10. So this is the NMR spectra. So this is for 9 proton, this is for 3 proton, this is for 4 proton. So now I will discuss about the splitting of the signal. So spin-spin coupling. So an NMR spectra shows a signal for each kind of non-equivalent proton in a molecule. So if you look much further, we find that the small spectra appear to be much more complicated than this. So let us consider system CH2. So let us consider this system CH2. So in this compound, like in which the single methane proton is very different chemical environment from the two methylene proton. So at the same time, here the methyl proton on the two terminals have a different chemical environment. So we expect 4 distinct signal for 4 sets of proton. Okay. So for this molecule, these CH3 are equivalent, these CH3 are equivalent, and this CH2 and the total 4 types of proton comes in the NMR spectrum. So obviously we have obtained 4 signals as expected, but 2 sets of methyl groups show sharp signal. These 2 sets of give the sharp signals, but with a single. Whereas the methane proton, means this H proton that come at 4.19, while the 3 peaks, and methyl protons come at 1.51 with 2 peaks. So this proton come at 2 peaks and this 3 peaks. So obviously, how can we explain this? So how these peaks come, 3 peaks come for this methane proton, and how these 2 peaks come for this H2 proton. So the answer is that due to the splitting of the NMR signal caused by the spin-spin coupling. The signal that is expected from each set is equivalent proton is appearing sometimes not as a single peak but as a group of peaks. Splitting actually reflects the environment of the absorbing proton with respect to the other nearby protons. So this signal that is expected from each set of equivalent protons is appearing sometimes not as a single peak but as a group of peaks. So splitting actually reflects the environment of the absorbing proton with respect to the other nearby proton. So that means, so splitting is due to the other protons that is close to the proton. So let us take the case of adjacent carbon atom carrying the respectively a pair of secondary protons and tertiary proton in compound like the BrCH2, CHBr2. At the first, consider the absorption of the secondary protons. So this is tertiary protons and this is secondary protons. So magnetic field of secondary protons is slightly increased or slightly decreased by the spin of the diverging tertiary protons. So the magnetic field is increased if the tertiary is aligned at the instant with the applied or the decreased if the tertiary proton is aligned against the applied field. So then the absorption of the secondary proton for the half of the molecule is shifted slightly downfield and the absorption of the other half of the molecule shifted slightly upfield. The signal of the splitting of two doublet is 1.1:1 with the equal peak intensity. So that means the magnetic field is increased. So that means for the secondary proton, if the tertiary proton aligned with this applied magnetic field, so the magnetic field will increase. If the tertiary proton is aligned against the applied magnetic field, that the magnetic field increases. The absorption of the secondary protons for the half of the molecule is slightly downfield, or adjustment of the other half is slightly upfield. So that means it's split into 1:1. equal peak intensity. So when the absorption is tertiary photon is considered, so this is a splitting pattern signal for the uncoupled photon when spin combination for adjacent CH. So it will one is the upfield, one is that downfield. The spin coupling one will give 1:1 doublet. So now when the absorption of tertiary photon is considered, so it is found that the photon is affected by the spin of the neighboring secondary photon. So, but there are two photons whose alignment in the applied field must be considered. So here we have now considered that a splitting of the tertiary photon with respect to secondary photon. So here the total two secondary photons. So we have to consider two sets. So there are four equally probable combination of the spin alignment for these two photons, of which two are equivalent at any instant. Thus, the tertiary photon fills one of the three fields at signal speed with three equal intensity. A triplet with peak intensity 1:2:1, 1:2:1, reflecting the combined probability of the two equivalent combination. So here, this two secondary photon will align into total four way. One is to both are uphill, one down, one down up, one down, and both are down. So here it will come as a 1:2:1 triplet. So the idealized NMR spectra of the compound here CH2 cell due to the grouping CH2 CH, the so 1:1 doublet from CH2 and nearly 1:2:1 triplet for CH as follows. So that's why this CH2 will 4.26 will split as a doublet, give this doublet peak, and here this CH is 5.79 will split as a triplet for this two H photon. So the total area under the doublet is twice the total under of the triplet. So little measure is also separation peak. The coupling constant in the doublet is exactly the same as the separation of the peak in triplet. So spin coupling is a reciprocal affair, and the effect of the secondary photons on the tertiary photons must be identical with the effect of the tertiary photon on the secondary photon. So that's mean the when there is the splitting of a peak, so the difference in the separation between these two peaks is equal for the secondary photon, and also the separation for this tertiary photon also the same. So even if they are applied to complicated spectrum of many adjacent peak, the identical peak separation would tell us the doublet and triplet are related. These two photons giving the doublet and one photon giving a triplet are coupled. Hence, they are attached to the adjacent carbon center. So, from this peak separation, we can identify the which photon is adjacent to the which photon. So that means both have the same coupling value in the NMR spectrum. So again, if we consider the systems like CH3, CH2, then due to the effect of the here CH3, here there are two types of photon. One is CH3, one is CH. So here the effect of CH group over CH3, we get then the 3H doublet with intensity 1:1, and but these three equivalent photons will be split the signal of adjacent CH photon to the four peaks with a coordinate which is 1:3:1. So obvious from the following data here, these three photons will have four types of alignment where three are upfield, two upfield, one downfield, two downfield, one upfield, and all are downfield. So here the peak intensity is 1:3:3:1 is a quadrant. So the NMR spectrum of this molecule here this CH3 will split as a doublet, will come as a 2.52, and here this CH is come as a quadrant, which is a 5.55. So the multiplicity and the relative intensity may be easily obtained from the Pascal diagram. So the multiplicity and relative intensity may be easily obtained from the Pascal diagram as shown in below, which is N is the number of equally coupled photons. So nuclei have the same chemical shift for the isotones and do not exhibit spin spreading. The spin spreading is observed only between the non-equivalent neighboring photons, that is the photon on the adjacent carbon having the different chemical shifts if the proton on the same carbon and a non-equal, they are also so coupling. So here, when one for one, there is the doublet for number of equivalent coupling equals 2. That should give triplet 1 is to 2 is to 1. When 3, it will give quadret 1 is to 3 is to 3 is to 1. When 4, it is give quintet 1 is to 4 is to 6 is to 4 is to 1 intensity. 5, 1 is to 5 is to 10 is to 5 is to 16. So let us consider some example which can understand the splitting pattern in NMR spectrum of a compound. Let us consider the 1,2 dichloroethane. So at first glance, it may be the adjacent at each methylene there are 2 protons on the adjacent carbon. So it will appear the triplet, but it is not as all the here. Only one type of proton. So all the 4 CH2 are homotopic. So that will come as a signal. Give one signal. So here for the 1,2 dichloroethane, we got only one single signal, but here no splitting pattern is observed because due to all the 4 nitrogen are same. So now if the case of this 1,3 dichloropropane, so 1,3 dichloropropane here total 4 protons, but here 2 sets of equivalent proton. One for these 2 CH2, there are one set, and this CH2 is one set. So there are 4 CH2Cl proton are magnetically equivalent, and these are adjacent to the non-equivalent 2 protons in the middle. So the CH2 group, thus for the 4 proton, the CH2Cl group therefore expected to appear is 1 is to 2 is to 1 triplet centered to the downfield around 2.50 with a double intensity with respect to the methylene proton in the middle. And the middle CH2 proton, one expected to appear in the upfield seat with the CH2Cl group at the around 1.80 quintet due to the splitting by 4 magnetically equivalent protons of the 2 CH2Cl groups. So that means here total 2, so one is 4 type of proton and one is 1. So these 2. So this CH2 is comparatively upfilled and it will speed due to this 4 equivalent proton. So here it come as a quintet, and this CH2 4 CH2 group come with speed by these 2 CH2 group that will come as a triplet, and it is upfilled compared to the CH2 group. So here this is the NMR spectrum of 1,3 dichloropropane. So here this CH2 come as 1.855. It's a quintet, and this CH2 has come as a triplet at 3.68. So obviously it is within limit of expectation. Just consider in case of isopropyl chloride. So here in the isopropyl chloride there are 2 sets of non-nuclear protons, 6 methyl protons and 1 methane proton. So now these 2 methyl groups are attached with the middle carbon having a single proton. Thus the methyl groups will be appear. These 2 methyl groups will be appear as a doublet due to the CH proton at around 1.60, whereas the middle CH it will expected to appear the downfield and respect to CH3 at 3.7 ppm as splitting by as a septate due to this 6 equivalent proton. So that means this CH proton as downfield compared to these 2 methyl, and it is splitting as a septate, and this CH3 proton is splitting as a doublet. So this is the in NMR spectrum. So here this CH3 at common 1.55 as a doublet, and here it is CH as a septate. So the intensity is to 6 is to 1. So now we have to consider the N-propyl chloride. So N-propyl chloride, there are total 3 types of proton. These 3, these 2, these 2. So here was 3 sets of non-equivalent protons. So we will get 3 signal in the NMR spectra. So 3 protons of this methyl group are expected to appear as a upfield as a triplet due to these 2 protons. So this is come as a triplet due to the 2 magnetically equivalent CH2 group, and two proton of these two proton of CH2 are expected to come as a triplet due to the two CH2 group and is a downfield due to the splitting. And now the two protons of these two methylene group at the middle is expected to appear the downfield with the methyl group and upfield with respect to the CH2 group as a multiplet due to in the presence of two magnetically equivalent protons on adjacent CH2Cl and other three magnetically equivalent CH2 So that means these CH3 has come as triplet for this CH2 and this CH2 come as a triplet for this CH2, but this CH2 group will splitting according to this CH3 or also this CH2. So this is come as a multiplet. So this is the NMR spectra. So here this CH2 has come as 3.63 as a triplet, and here this CH3 comes as 0.90 which has a triplet, and this CH2 comes as a multiplet at 1.61. So peak intensity is 2:2:3. So we have pointed out that if the proton on the same carbon are non-equivalent, they may also show the coupling. Let us consider some example. As example is a 2-bromo propene 1D. So here in this molecule we have three non-equivalent protons. This CH3 you have one, this H and this H. The methyl proton actually appear as a singlet. Here, as there is this methyl as a comes as a singlet, and this carbon has no proton on the adjacent carbon. Why is this? The vinyl protons are expected to appear as a doublet because of the presence of another non-equivalent proton in the same carbon. So these two CH are not equivalent. So this H come as a doublet due to the splitting of this, and this H also come as a doublet due to the splitting of this H. So this is the NMR spectra. So here this CH3 come as a sharp signal peak, and this H come as a doublet, and this H come as a doublet. So peak intensity is 1.1:3. So next, this 1,2 dibromo ethene. So here total only one set of protons. So two vinylic protons will appear as a singlet. There is no question of splitting, as there as these two vinyl is equivalent. So thus, according to the NMR spectra, so here only brought one sharp single signal is observed for these two CH2 H group. This has two equivalent. Now, if we consider this bromoethene, is vinyl bromide. So here also total three sets of non-equivalent proton. So we have to observe, we may observe total three signal for in the NMR sector. So the vinylic on the carbon being in this bromo group is expected to appear the downfield in comparison to the other non-equivalent vinylic protons. Since all these three vinylic protons are non-equivalent, it is expected that each will appear as a doublet of doublet, as for the each proton have two magnetically non-equivalent proton on the adjacent carbon on the same carbon. So that means here for this CH group, it will first be according to this doublet, then this doublet also split by this hydrogen. So that it gives doublet of doublet splitting pattern. So same case for this hydrogen, it will also give doublet of doublet, and this hydrogen also give doublet of doublet. So it is the NMR spectra. So here this is a doublet of 6.32, this doublet give 5.80, and this is a doublet of 5.70. So in above, we are particularly interested in the splitting pattern of the aliphatic compound. In the aromatic system, two non-equivalent protons on the adjacent carbon in ortho orientation undergoes spin-pin coupling, which in open referring to ortho coupling. Similarly, meta coupling is also known. So we have to look on the following aspect of ortho meta coupling. It will be clear. So here for this molecule, there are total four sets of non-equivalent proton. So this CH3 has come as a singlet, downfield 2.34, and this CH3 is comparatively the downfield compared to this CH3, and this also comes as sub signal, and this hydrogen will this two hydrogen is a downfill in the aromatic region, give the rise 7.91, and this hydrogen is first splitting by this hydrogen, and this hydrogen is found in this figure. So this is come as a doublet. This also comes as a doublet. So now for this case, so for this molecule, here total also 4 type of non-equivalent proton. So this CH3 come in the single signal. So this will come as a 2.15. This for this CH2 compare downfield, and here these two hydrogen are not in the adjacent to the adjacent. So here this hydrogen also come as a no splitting observed for these two hydrogen. So now for this molecule, this CH3 is come as a single no splitting pattern observed as a single sharp signal, and this CH also come as a sharp signal and no adjacent hydrogen atom. So it is given 8.3, and for this CH2 are splitting each other, so it will come as a doublet. It will also come as a doublet. So this keep the doublet pattern. So thus keep in mind that peak area reflects the number of observing photon, and the multiplicity of the splitting reflects the number of neighboring photons. It is possible to find out the structure of any compound from its NMR spectra, provided the course of Wheeler concept DBE double bond equivalent structure feature of the compound, such as the functionality necessity of the position in an spectra. Above we have the instruction. However, we have shown the number of NMR spectra of similar compound which may exist or not. Maybe that hypothetical one. To understand how we have given a spectrum of a simple compound in a laboratory intermediate for an antimicrobial study of the carbon derivative. So this is the NMR spectra of the one molecule. This is also one molecule. So here thank you.